In electrical engineering, we often encounter periodic waveforms that aren't simple sine waves. The sawtooth wave is a common signal used in power electronics and synthesis. Understanding its average value is crucial for determining DC equivalence and circuit behavior. A sawtooth wave is characterized by a linear increase in voltage over a specific period, followed by an instantaneous drop back to zero. This repetition creates a pattern where the voltage is a direct function of time within each cycle. The average value of any periodic waveform is defined as the integral of the function over one full period, divided by the duration of that period. Geometrically, this represents finding the area under the curve and leveling it out. To solve for the average, we first need the mathematical expression for the ramp. Since it starts at 0 and reaches peak voltage Vp at time t, the slope is Vp over t. This gives us the function v of t equals Vp over t times t. Before we dive into calculus, let's use geometry. One cycle of a sawtooth wave forms a right triangle. Calculating the area of this triangle is a shortcut to finding the integral, providing an intuitive check for our final result. Now we substitute our linear function into the average value formula. Since Vp and t are constants for a given wave, we can pull them outside the integral, leaving us to integrate the simple variable t with respect to time. Applying the power rule of integration, the integral of t becomes t squared over 2. We then prepare to evaluate this expression at the boundaries of our period, from 0 to the full time t. Substituting the upper limit t into our expression gives us t squared over 2. Subtracting the lower limit of 0 leaves us with a clean algebraic term. Notice how the t squared terms are now positioned to cancel each other out. The t squared terms cancel out completely. This leaves us with a very simple and elegant result. The average value of a sawtooth wave is exactly 1/2 of its peak voltage. This confirms our geometric intuition from earlier. If you look at the waveform, the horizontal line at half the peak height perfectly bisects the triangle. The area of the triangle above this line fills the empty space below it, creating a steady DC equivalent level. Let's apply this. If you have a sawtooth signal with a peak of 10 volts, its average value is simply 5 volts. This is the value a standard DC voltmeter would measure when connected to this signal. Even if we change the frequency, the average value remains dependent only on the peak. For a 24-volt peak signal, the average is 12 volts. The duration of the period t cancels out, making the result frequency independent. Comparing this to a rectified sine wave, which has an average value of approximately 0.637 times the peak, we see that a sawtooth wave delivers less average voltage for the same peak height. Note that if the sawtooth wave is symmetric, swinging from a negative peak to a positive peak, the average value over a full cycle is 0. This is because the positive and negative areas cancel each other out. To summarize, the linear nature of the sawtooth ramp means its average value is always half of its maximum height. Whether using calculus or geometry, the result is a consistent ratio of 0.5. Test your knowledge. If a sawtooth wave starts at 0 and reaches a peak of 50 volts, what would be the average value? Think about the ratio we just derived. The answer is 25 volts. By simply dividing the peak by 2, we find the DC average. Thank you for watching this lesson on waveform analysis. Generated by Vision Solve AI.